Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will solve certain problems on duct design. Before we solve any problem on duct design, I would like to discuss the air handling units. The air handling units are nothing but the fans or blowers. Okay, it can be a single fan or a bank of fans, and fans can be connected in series. Suppose very high pressure is required, then fans will be connected in series. If high flow is required, then fans will be connected in parallel. Now suppose pressure drop in a fan delta P is equal to half K rho V square. Now this is P1 and V1. This is P1. Now delta P2 is equal to half K2 density same V2 square and so on. We have delta Pn is equal to half Kn rho Vn square. Right? Now total pressure or equivalent pressure, that is delta P, is going to be equal to half K1 rho Q. Discharge is same because when they are connected in series, discharge is same, Q by A1 whole square plus half K2 rho Q by A2 whole square and so on. And then delta P can be written as sigma K rho by 2 A square Q square. This is, you can find this analogous to delta V is equal to IR. Sorry, either it is reversed. R into I. Now this I equivalent to analogous to Q square, and this is resistance and this is potential difference. Now if they are connected in series and if they are connected in parallel, how the pressure and discharge are going to be affected? Suppose they are connected in series. Delta P is equal to R1 Q1 square plus R2 Q2 square and so on, and delta P itself is RQ. So RQ is equal to Q square is equal to R1 Q square. Now it is not 1, 2, 3 because they are connected in series. Discharge is same, volumetric discharge is same, R2 Q square and so on. Now this Q will be cancelled out and R is equal to R1 plus R2 plus R3. So if we have the value of R1, R2 and R3, if they are connected in series, it will be total R will be algebraic sum of these values of R. Now suppose fans are connected in parallel. If fans are connected in parallel, in that case delta P is going to remain constant and Q is equal to Q1 plus Q2 plus Q3 and so on. This is 1, 2, 3. And if there are more numbers, then it is going up, it can go up to n. Now Q, we know that it is delta P upon under root delta P upon R, under root delta P upon R1 plus under root delta P upon R2 plus under root delta P upon R3 and so on. So if they are connected in parallel, then equivalent resistance will be 1 by under root R1 plus 1 by under root R2 plus 1 by under root R3 and so on. That is one thing. Second is, if you remember in earlier lecture, I told you that equivalent diameter in a duct is 1.3. If it is a rectangular duct, then AB raised to power 0.625 divided by A plus B raised to power 0.25. Right. In this case, if we take friction loss in a duct, then it is equal to half rho V square by D multiplied by F, friction coefficient, and that is equal to half F rho V square by T. Now delta P upon L, if this friction is constant, this is also constant, it is equal to V over D, and that is equal to V square is nothing but Q by A whole square, and D is, again we can take A, and P is perimeter. This is proportional to product of these two. Now in a duct system, if we take the equivalence, in that case we assume that this is constant. When this becomes constant, then discharge through duct becomes proportional to AQ by P. A is the cross section area, P is the perimeter. Now we have two ducts, one is rectangular having side A and B, another is circular having diameter D. Now if the friction loss in both the ducts is same, coefficient of friction in square and in the rectangular and the circular duct is same, density of the air is same, then AQ by P in a rectangular duct or a circular duct is equal to AQ by P in a rectangular duct. Now further, A cube is pi by 4 d square divided by pi d cube. Sorry, no, it is not this cube, it is A cube. So cube is equal to A cube is AB cube divided by 2A plus B. This is the perimeter of this rectangular duct, and this is the cross section area of the rectangular duct. Now if we simplify this, this is going to be equal to d raised to power 5 is equal to 32 divided by pi square AB cube by A plus B, and here D is equal to equivalent diameter is equal to 32 by pi square raised to power by 1.5, AB raised to power 1.5 is equal to 3 by 5, A plus B raised to power 1 by 5. Now here D, again D equivalent, this is D equivalent is equal to 32 by pi square raised to power 1.5 is going to be equal to 1.265 AB raised to power 0.6 and A plus B raised to power 0.2. Now the average velocity are not same. If you look at the average velocity in the square duct, this rectangular duct and this round duct are not same, and with the help of some experimental investigations also, this formula is modified as D equivalent is equal to 1.3 AB raised to power 0.625 divided by A plus B raised to power 0.25. This is how we get this formula, and this formula is very useful if we know the value of A and B. If it is a square duct, then definitely A is equal to B. So if equivalent diameter is known to us, A is equal to B, we can find the value of A and B. If there is a rectangular duct, then we must have the aspect ratio, sorry, A by B, and then we can find the value of A and B. Or in some of the cases we say, okay, depth of the duct is restricted to 500 mm. Now depth of the duct means B is 0.5 meter, and then we can find the value of A. So, there are several ways of finding out the dimensions of the duct once we have the equivalent diameter of the duct. Now, we will take one live example. Suppose I have to design a duct. I have to design a duct and I assume any duct network. I assume any duct network, and duct network, let us say there is a pump, that is one opening A, another opening B, third opening C. Let us have this duct, and losses in the bending are compensated by the duct length. Okay. So, here we will not consider losses in change in the direction or dynamic losses in this duct network. Now, suppose in this duct network we can have, okay, let us take the simple example. Now, here in this case I want to have certain discharge, let us say here 200 meter cube per minute, at B let us say 150 meter cube per minute. Here we can take let us say 400 meter cube per minute. So, there are three openings. Duct network can be a very complicated diagram. I am just taking one simplified system so that you can understand how the duct system is designed. So, we have taken only three opening ABC. We can have more opening also here. Let us say this A, B, C, D, E, right. So, C there will not be opening, then D, E it is again bifurcated 200, something like that. We can have a network, but for the sake of understanding of the design process, we have taken only three openings. Now, in this case some minimum velocity has to be maintained in the main duct. This is the main duct. So, this is OA. A minimum velocity is required. Suppose the airflow in duct is very low. In that case, first of all the size of the duct will increase, and some microorganisms may also develop, especially this happens in the when there is a bend in the duct. Some stale air remains, some dead air remains in the corners of the duct. Suppose there is a sharp turn. So, in the corners of the duct here some stale air may remain, and this may provide grounds for the development of microorganism which is not desired. So, some minimum velocity has to be maintained. Some minimum velocity in the duct has to be maintained. Suppose here we are maintaining 7 meter per second. 7 meter per second velocity is maintained. So, first of all we will take the total discharge. Total discharge Q is how much? 400 plus 200 plus 150. It is 750 meter cube per minute. Now, this 50 meter cube per minute has to be converted into liters per second. So, that is going to be 750 into 1000 divided by 60. And this is 12.5. So, 12,500. That is 12,500 liters per second. Let me check with the calculator also. 750 into 1000 divided by 60. Yes, 12,500 liters per second. Right. Here, now for this discharge, we have this 7 meter per second velocity, 12,500 discharge, right. Friction, yes, duct friction. Suppose we are we have adopted this constant friction in the main duct and in the branches, that is 1 Pascal per meter. And this 7 meter per second is minimum velocity. So 7 meter per second minimum velocity, then we have two riders. So we will remove this rider, 7 meter per second. Initially we will remove this rider. We will have only 1 Pascal per meter, 1 Pascal per meter and this much of discharge. So for 1 Pascal per meter and this much of discharge, this is approximately 12,500, right? And 1 Pascal per meter. 1 Pascal per meter is this much. So we will be getting this point, right? Now here you can see the velocity is already more than 7 meter per second. So we wanted to ensure that the velocity should remain. I mean, it is not part of this problem, but velocity remains more than 7 meter per second. So here, if you look at the velocity, velocity is 12 meter per second in the duct. 12,500 we have taken here. This is the point for O, right? Now OB, no, not OB, it is no A, B, C, now O, D, and their joints is E. So diameter of OD. So diameter of OD, if I have to calculate diameter of the OD, then diameter of the OD is between this 1000 and 1250. So let us say 1150 mm. We will be getting diameter of OD. Now dB, dB is also 1 Pascal per meter, but the discharge is 150. So for 150 QB, 150 meter cube per minute, so it is 1000 multiplied by 60, 2.5, 2500. So we will look for the discharge of 2500. So 2000, this is 3000, 2500 will come somewhere here. This is a log scale, 2000, 3000, 2500 will come somewhere here. And from 2500 again we will draw a vertical line and we will locate the point, and this is going to be the diameter of the duct, and that is going to be equal to OD. So DOD, so dB is going to be equal to 630 mm. Similarly, diameter of DE. Diameter of DE is, the flow through DE is, total flow is 750 minus 150, 600 meter cube per minute, or it is going to be how much? 10,000. Flow through dB is 10,000 liters per second. So again 10,000 we will look for, and at 10,000 liters per second we will take the diameter here. It will come straight away, it will come here 10,000. So it will come here, it will be around 1050. So diameter of DE is equal to 1050 mm. Now again, how much air is remaining with us is 600 meter cube per minute. Out of this 400 is going to this side. So if I want to find the diameter of CE, right, then 600, out of 600, 400 is coming to this side. So 400, again I will convert 400 into liters per second, then it is 1000 divided by 60, sorry 1000. So 400 into 1000 by 60 is will be 400 into 1000, 60 is going to be 6666. So 6666 666 will come somewhere here, and then we'll go get a diameter. This is 800 and this is 1000, so it is going to be 875 mm. So DEC 875 mm. Likewise, we can calculate all the diameters, right? So diameters of all the duct can be calculated in this way. Now pressure drop. Now for pressure drop, in order to have pressure drop, we should have the length of the duct. And pressure loss in due to change in the direction or the dynamic pressure loss has been compensated by increasing the length of the duct for the sake of convenience. Suppose this length is 10 meter, this is 50 meter, and this is 60 meter. This is 20 meter and this is also 20 meter. Now in this case, pressure drop, total pressure drop in the longest duct will be 10 meters plus 50 meters plus 60 meters multiplied by 1 Pascal per meter, that is the pressure drop per meter length, and it is going to be 120 Pascal. Now pressure drop between O to A is 120 Pascal. Pressure drop between O and B, delta P OA is this, and delta P OB is going to be equal to 10 plus 20 into 1 is equal to 30 Pascal. So pressure drop between this and this is 30 Pascal. Pressure drop between this and this is 120 Pascal. Now in this case, what is going to happen? If we take pressure drop of 30 Pascal and duct diameter we already calculated. How much we calculated the duct diameter here? 1150. No, dB we have not calculated, okay. So if you look at the pressure drop between this and this, so definitely pressure drop here is less, length is less, most of the air will try to leave at B, so we will have to provide dampers. So between this point and every outlet, the pressure drop has to remain constant. So this additional 90 kilopascal will come through dampers. Otherwise, what is going to happen? The most of the air will be short circuited. Now we can make the circuit damper free. We can make the circuit damper free. How we can do that? We can do that if we assume that delta P between dA is equal to delta P between dB. Now delta T between dA is 110 Pascal, and delta T P between dB is, suppose, delta P dB. This should be equal to delta P dB, and then we can say that the per unit length pressure drop delta P by L dB can be 110 divided by 20. So that is going to be equal to 5.5 Pascal per meter. So instead of providing a damper, we can reduce the diameter of the duct. That I will show you how. So for 150, for equal friction method, diameter of dB is equal to 150 into 1000 divided by 60. So 2.5, 2500. So 2500, 1. So this is 2500. 2500, 1. Diameter of dB was 630. 630 mm diameter of dB for equal friction method. Now what we have done, we have assumed that pressure drop between D and A and D and B are same, and then pressure drop per unit length between dB is 5.5 kilopascal. So instead of coming here, again we will have to go up to 5.5. It will be somewhere discharge. What was the discharge? 2500. So it is going to be 5.5. 5.5 something somewhere here. On the same line, simply the discharge will be something like this. So here you can see the diameter of the duct has reduced to only 425 mm. Diameter of dp dash is equal to 425 mm. Here the diameter is 630 and it is reduced to around 425 mm, and if you reduce the diameter then we do not require damper here. So this is how this network can be damper free also. There are many more networks. If you look at the books, you will find a number of duct networks, and you can use this chart for duct design for those networks. That is all for today. Thank you very much.